So welcome back after Diwali vacation. Hope your exam was good mid-semester and very soon you will face end semester. So before I start the actual course uh, related to multi-layer, so we will have a problem on a two-layer network. See this network, there are two layers. Say this is layer 1 and this is layer 2 with only one neuron. Now the question is, find out the region where seventh neuron, this is TLU7, gets fired. So find region where TLU7 gets fired. Okay, so this is our problem. So we have to show on x1, x2 plane. So there are two inputs here, x1 and x2. So I can draw like this, x1 and x2. So you have to mark the area where TLU7 gets fired. So that is our question. So we can see one by one what these individuals are doing, and then we can find out where is the region there this TLU7 gets fired. Now you can see threshold here is 3.5. So if net value here is greater than 3.5 or equal to 3.5, then this is going to produce +1. Okay, so to happen this thing, we have to check what these individuals are doing. So when this net will be more than 3.5. So if I can find out that, then I can say that this is the region. So what we will do, we will find out individually what these previous layer neurons are doing. So we can take this first neuron, that is threshold logic unit 1, and there it is written as threshold equal to A. Now this is given to us, assume that A is less than B is less than C is less than D, and for x2 E is less than F. So you can see here there are two thresholds, E and F. So here for x2 E is less than F. So this is given to us. So this is given data. Now we take neuron number 1. You can check here for neuron number 1, threshold is A, which is the minimum possible threshold in given problem. You can see that A is less than B is less than C is less than, say, D. So this is the minimum one. So along x-axis, I will keep A here and try to see what this neuron number 1 is doing. Okay, it has weight associated as 1. Only one input is going here, that is x1, and threshold for comparison is A. So what is implemented here is, this is x1 and you are comparing with A, so the net here is x1 minus A. Okay, so when this threshold logic 1 will fire whenever your net is more than A. So whenever x1 is greater than A, this neuron is going to fire. So see the situation here. So this is my position A, and what this neuron is suggesting me, go this side so that I can get fire. So you have to be this side so that neuron number 1 will get fire. Okay, otherwise it will produce say -1. If it is firing, then it will produce +1, and say it is not firing, then it will produce, say, -1, assuming that neuron is bipolar, binary kind of a thing. Okay, so neuron number 1 is saying go this side. Then I take, suppose, neuron number 2. Say this is my input going to neuron number 2. So what is implemented here? You can see here the net coming over here is x1 and compared with -b. Okay, or compared with b. So the net coming to this neuron is x1 minus b. So whenever your x1 is greater than b, actually this will get fire. But you can see there is a twist here. You are multiplying with -1. Okay, so that means you are making the things in opposite way. So actually, so whenever you are more than b, your output is +1 here, but it will get multiplied with -1. So in fact it will produce -1 here as output. That means if your x1 is less than b, then this neuron is not fired. It will produce, say, -1 here, and -1 multiplied by -1, it will produce +1. So in fact what is implemented here is this particular line, and what this second neuron is saying, go this side. First neuron, what it is saying, go this side. Second neuron, what it is saying, go this side. Okay, so if your input is somewhere here, both neurons will get fired. Understood? So what is implemented by second neuron is threshold unit x1 minus b multiplied by this minus. Okay, so this is the implementation of second neuron. Now like that, we can go for neuron number 3. So this is implementation of neuron 1. This is implementation of neuron 2. This is third one, and this is fourth one. Okay, so if I go to that figure, you can check here when this will fire. What is implementation here is x1 minus c. So threshold unit x1 minus c. So whenever x1 is greater than c, this is going to fire. What this fourth one is doing, it is taking x1 comparing with d. So x1 minus d thresholded, and you just see this -1, so multiplied by -1. So this is implementation of fourth neuron. So when this will fire, whenever your x1 is less than d, this is going to produce +1 here. Since at this position, whenever x1 is greater than d, actually this will get fire. It will produce +1, but it will get multiplied with -1. So what I want here +1. So if my input is less than d, then this will produce -1. This -1 will get multiplied with this -1, and it will produce +1. Okay, so in short, if I want to say when this terminal will produce +1, it will produce +1 whenever x1 is less than d. So this will produce +1 whenever x1 is greater than c. Then what about this fifth neuron? So you can see here x2 is coming, getting multiplied with -2, and it is getting, sorry, -1 getting compared with -f multiplied by -1. Okay, so how it will look? What is net value here? So net value here is -x2 x1 getting multiplied with minus 1 minus x, it will be minus x2, and minus 1 multiplied with minus f, so it will be plus f. So this is the net coming to this neuron. And what is the implementation? It is the thresholding of this, so minus x2 plus f. Okay, minus x2 plus f. So when this will get fire? When this will get fire? Can you think? So when I go to the fifth one, so it will say go this side. Okay, go this side. I think this should be plus. What about the last sixth neuron? It is saying x2 minus e. So go this side for firing me. So first neuron is saying go this side. Second neuron is say go this side. Third neuron is saying go this side. Fourth neuron is saying go this side. This is fifth and this is sixth. Now we have to find out the region where the net input to the seventh neuron is greater than 3.5. Now if you take, suppose your input is lying over here, then you can see that first neuron is satisfied, second neuron is satisfied, third is not satisfied, fourth is satisfied, fifth is satisfied, sixth is satisfied. So one input is not satisfied. So what is total sum here? There are 5 neurons that are fired. So sum is 5, and one neuron is not fired, or it is producing negative output. So it is minus 1. So net value is 4, which is greater than 3.5. So when you stand here, anywhere in this region, your seventh neuron is plus 1. Okay, so that is what we want. The region where seventh neuron is getting fired. Now suppose you stand here, what will happen? If you stand here, say here, then this is satisfied, this is satisfied, this neuron is not satisfied, this neuron is satisfied, this is not satisfied, this is satisfied. So 1, 2, 3, 4 neurons are fired in positive sense, and 2 neurons are fired in negative sense. So 4 minus 2 is 2, so which is less than 3.5. So finally, last seventh neuron is not satisfied or not fired. Okay, for this region, for whole this region, it will not fire. So you can keep on checking like this for all the regions. What is going to happen? So you'll find that this area and this area, if your input is anywhere within these two boxes, your circuit is going to fire. You can check here. Suppose you are standing here, then this is satisfied, or this neuron is satisfied, this is okay, this is fired, this is fired. Now this will be firing because you are ahead of this, and this is not fired. Again, one input is minus and all others are plus. So 5 minus 1 is 4, and this will fire. So you will see that for the rest, anywhere throughout this space, last neuron is not satisfied. Okay, so this is clearly a region submerged in, say, class 2. Say class 1 is completely surrounded by class 2. See, I can call this as suppose class 1, and I can call this as class 1 because here the final output is plus 1. For others, the output is minus 1. So plus 1 region is completely surrounded by the other class. So I can say class 1 is submerged in class 2. So this is totally a non-linear problem. I cannot draw a single line to classify such regions. That means suppose I draw, so this is class 1 region and this is also class 1 region and rest is class 2. So all these are class 2 regions. So I cannot draw one line so that these classes are separated into two halves. Okay, suppose I draw like this, what will happen? If I draw like this, then this region is suppose class 2 and this region is a class 1, then all these samples are misclassified, and for other thing this region is misclassified. So there is no solution with a linear uh, kind of a thing. We have to have a solution such that our implementation uh, can handle, say, nonlinear data. So this is the final solution. Now, thing is that we have done or we have seen manually how we can do this with the help of two layers. Now we will see now the next part of this, how we can do this automatically. That means how one can construct such circuits or networks which can learn nonlinearity automatically. The important thing that we have seen from the previous example is that if I use more than say two layers or at least two layers, then I can handle nonlinearity. We cannot handle nonlinearity using single neuron or perceptron. We have to have at least two layers so that we can handle it. We have also seen XOR problem in previous classes where similar concept was uh, explained. Now we are revisiting the delta learning rule, which is R equal to D minus O, that is output here, into F dash of net or F dash of output. So complete change in weight is given by C into D minus O into F dash of net into input, that is X. Now we have seen what is delta learning rule in previous classes. We will apply some input like this. We'll calculate net, then we will pass this through some activation function which is differentiable because we want differentiation of that. So maybe sigmoid kind of thing or logistic activation function. So we can pass through that and output is computed. It is compared with desired response because this is a supervised learning. So we will expect that it should produce some desired response for given input. So that will be, output will be compared with that, and error signal is propagated in reverse direction, and we require f dash here, so we calculate f dash, and this signal is used to change the weights. So this is known to us in earlier lectures. Now based on that, we are going to see very popular algorithm of neural networks, artificial neural networks, called as backpropagation. So those who can understand, or those who have understood backpropagation, I say that they have understood the basics of artificial neural network. So this is a must rule in current uh, neural networks, artificial neural networks. So try to understand what is the concept and how we can use this for solving different kinds of problems. So this is the algorithm based on error gradient. The concept of error gradient we have seen while deriving this delta learning rule. Say there is some say mountain like this, say mountain of heights. Say there are say locus of points where we have different heights, and if I take gradient of height, it will give me a direction where there is a steepest path, in which direction the height is changing with maximum rate. Now similarly, if I take some error surface like this, and if I take gradient of this, suppose I am standing here, then it will give me the direction. Suppose I am standing here, then the direction where error is increasing rapidly. But I want the direction in opposite side because I want to reduce error. So I will take negative gradient of error as my direction. So I will move in this side. So this is the negative of gradient of error. So based on this principle, we are going to uh, train our networks. So error is here difference between the actual output and desired response. Okay, so the difference between that is used for creating error signal. So change in weight with reference to negative gradient of error is used to train the network. So how it is used, we will see quickly. So what is basic idea here is that suppose this is my input X, this is say layer 1 like our previous problem, and there is another layer of neurons, and this is the output available. So what we do, I feed my input. There are many neurons here. They will produce their own output that is propagated to next layer and given as input to the next layer, and it will produce its own output. So this is my final output at the last layer. Here we are going to compare this with our desired response D. Okay, so whenever I have a desired response, that means it is a case of a supervised learning. So I will find out D minus O as my error signal, suppose, and if there is some error, then I will use that to change weights here. Now if you remember this change in weight for delta learning rule, it is C into D minus O into F dash into input. Say for this L2 layer, suppose this Y will act as some input and X is input for layer 1. So when you try to find out weight updation, you can directly calculate for L2 because at this last layer we have desired response available, output available. We can calculate F dash here, and then we can change weights directly. Now if I want to use same rule at this layer, what is the problem? The problem is that at L1 layer we have no desired response available. Desired response is available for only for last layer. Okay, we don't know what should be output at this level because the data is such that we will supply X and then desired response. Suppose there is a feature of pen, then I will say, okay, this is a pen, and height is say some 10 centimeters and width is 1 centimeters. So 10 comma 1 and its label pen, maybe say class 1 is +1. So this is available. Okay, but I am using suppose 2-layer network, then what should be output for second layer is not available. If you have suppose many layers like this, say L1, L2, L3, L4 and so on, in case of a deep network you have this situation. So you have input here, you have desired response here and output here. So you can easily update this layer, no doubt, but you cannot update weights for hidden layers. Now question is how to change weights for hidden layer. So we have to have a small derivation for this. We will find out how to do this and then we can use that formula everywhere. Now concept for this is that if this is the situation, you have to train say 2 layers or more layers. What we are going to do is we are going to use our simple delta learning rule for last layer, and for hidden layers what we are going to do is we are going to create or generate some delta signal, which is actually error signal. That's why the name of this learning rule is delta learning rule. So this delta signal based on d minus o is computed for last layer, and this delta is used to change the weights in hidden layer. Suppose there is one more layer here, say hidden layer 2, say L1, L2, L3, suppose like this, then this delta is also propagated in reverse direction to update weights here. So delta computed at output layer is used to change the weights for hidden layer number, say 1 from this right hand side. I can say delta y here, and this delta y is used to create some error signal for previous layer. Okay, like that. What I mean to say is some delta signal is created for output layer, and this delta is propagated in reverse direction to train or update weights for hidden layers. So once you compute delta for output layer, you can use that delta to find out error signal for hidden layers. Then you can update easily. Okay, so how this is done, that we can see with some small derivation. Now suppose I take very simple structure to understand the things, and let us say this is my input here X, this is some output Y1 to Yj for hidden layer. So this is input, this is output layer, and this is hidden. Okay, now the weights associated here for output layer, I will call that matrix as W matrix, and weights associated here for hidden layer, I will call it as V matrix. Okay, so input X is supplied, then net is calculated here for each neuron, and then it will be passed through some activation function. It will produce y1, y2 up to y capital J. This is getting multiplied with W matrix for output layer, and it will be passed through again some activation function, and it will produce output O1, O2, O3 up to O capital K. So here K is equal to number of classes we want to learn. Suppose we want to learn 10 classes, then there are 10 nodes in the output side. How many nodes in the input side? So it depends on what is input feature length. Suppose you are extracting two features for some problem, then there are two, say, nodes in the hidden input side. If your data is extracting, say, 15 features for a problem, then you have 15 input nodes for this network. So number of input nodes is equal to number of features. Okay. Then how many hidden nodes? So it totally depends on your choice actually. So for this particular derivation, I am saying there are capital J number of neurons. As a thumb rule, in general, what you can try with is use twice number of say neurons, twice number of neurons of that feature vector. Suppose your feature vector is of size 5, then try to take some 10 neurons in the hidden side. Output how many? It depends on how many classes you want to learn. So I want to learn 5 classes, then use 5 neurons at the output side. Now this is the structure. So there are some weights associated here. Weight. Classes. Now what we will do, we will start our derivation with output side, because we can update our output using our normal delta learning rule. Now why to use normal delta learning rule, that we'll see again through the derivation. Now if I consider the last layer, structure is like this. Say these are hidden say nodes, and output of this is connected to all the neurons in the output side. So there are O1 to O capital K neurons in the output side. Now how to change weights for last layer? Let us take some kth neuron, say kth neuron, say this is small kth neuron, and if I zoom this area, then it has its input y1, y2, y cap small j up to y capital J. Okay, and this is the net for this particular neuron, say small kth neuron. So wkj is the weight between, say, this kth neuron and jth input. So we write wkj for the weight between kth neuron and small jth input. Suppose I write W3 5. What it means? It is the connection or weight for a connection between third neuron, say this will be third neuron, and fifth input. Okay, so Y5. like that. Now, first of all, we will define error for our problem. So error for our problem is defined like this, is half into k equal to 1, small k equal to 1 to capital K, that is dk minus ok square. So this is squared error. So we are defining square error as our error signal. So what it means, you will take your input, you will apply your input to all the neurons, you will calculate output for all the neurons, and there will be output 1, output 2, output K, output capital K. For each node there will be some desired response, D1, D2, like that up to D capital K. So what I am going to do is, I am going to say error is equal to half multiplied by D1 minus O1 square of that, so that it will be always a positive number, plus D2 minus O2 square, plus and so on up to D small k minus O small k square, plus and so on up to D capital K minus O capital K square. Okay, so if I do the calculation of difference for each node and square it and add the error signal here for individuals, and just multiplying by half so that it looks like some energy signal. So you can drop even half here, but it is kept intentionally, that you will come to know when I do this derivation. So time being, just forget about half. What you are doing, you are taking difference square and you are calling that as error signal. Assume that all the neurons are producing correct answer, then this dk minus ok for all the neurons will be 0. That means error signal produced is 0. Whenever dk is not equal to ok, there will be error signal. Now, as per our principle, we are going with negative gradient of error. Negative gradient of error, then we can use that direction for changing the weight. So this eta stands here for a learning constant. So this is a learning constant. Okay, so negative is the direction that we want to travel. Now if I differentiate this equation number 1, or partial differentiation of this equation number 1 with respect to, say, weight wkj, so that will be equal to dou E by dou wkj, and then I am taking the help of chain rule. Okay, I think our time is over. What I will do is, I will start this derivation tomorrow from scratch. Okay, from this slide I will start this again, so that things will be in flow. Otherwise our derivation will be half, and then I have to explain it again. So I will stop here, then I will start this derivation from tomorrow. Okay.